Okay, so midterm grades have been posted. The class average was maybe like a 77. If you would like to see your midterm, just send me an email and I'll bring it to office hours. You can review it. Otherwise, that's that. And so today we'll cover Chapter 7, and next week you will have a quiz covering today's stuff, Chapter 7, okay? So, okay. So Chapter 7 is on what we call sampling distributions, okay? Okay, and so I guess before I get into Chapter 7, this is coming with an understanding or an assumption that you guys understood Chapter 6, which was about the normal distribution. And I think for a lot of you that is true, but I also know, well, based on what I saw on the midterm, I know several of you do not have a good understanding of Chapter 6, or it did not. Your understanding of Chapter 6 was did not come across in the midterm, and so you know, if you struggled with Chapter 6 and the normal distribution, please, you know, take the time this week to make sure you can handle that stuff. Okay. All right, so the idea behind a sampling distribution, let me describe what we are dealing with. Okay, so we can start off with a population, okay? And the population is just kind of this big entity that is too big for us to observe directly, okay? And the population, maybe we are going to look at a categorical variable. Yes?
It's very dark. Can you make it lighter?
The screen or the...
It's darker than it usually is.
Is it? I mean,
Oh, it's these
Lights. It's the light. Is it?
Oh, I've turned off the lights. I don't know what I can do. There's no brightness option for...
I feel like it's usually lighter.
I don't know. Let me see. Okay, I'll I can try turning that projector on also if you want to look at that corner there. Okay. So okay. So let's say we are talking about a categorical variable. Okay. And so as far as the categorical variable goes, the population is defined by a proportion, okay? So the population has a proportion P. Okay, so maybe our example, imagine this to be a big bucket or a big kind of like a tub, and here I'm going to just fill up this tub full of M&Ms. Okay, maybe like 100 pounds of M&M candies or something like that. And in this tub, we could count exactly how many pieces of candy we have and count exactly how many of these candies, let's say, are red, okay? And we can calculate exactly what proportion of M&Ms in this tub are red, okay? So maybe we find that exactly 0.165 are red, okay, in this tub. And so that means, as far as this tub goes, the proportion of red M&Ms is 0.165, okay? So this could be, you know, I've counted up 100,000 pieces of candy or something, and 16,500 are red. Okay, so my proportion is 0.165. Okay, so this is our setup. We've got a population. And what we are going to do is from the population, we draw a random sample. We take a random sample, okay, of size n, okay, and the random sample has proportion p hat. Okay, so for example, this is a big tub of M&Ms. I'm going to, you know, kind of mix it up, and I'll take a scoop of M&Ms out, okay? So I take a scoop out. Maybe in this scoop, I take n equal to 200 pieces of candy. And if I looked at how many are red, what proportion of red candies might I see? Would I get exactly 0.165? Maybe, so something around there. So maybe my p hat for this random sample, let's say, is 0.18. Okay, so I get 18% red. I don't know, okay? And so I record this value, p hat, okay? And then what we do is we go to the population again, and we draw another random sample, okay? We'll call this sample 2.
Isn't 0.18 bigger than 0.165?
Yes, yes.
So how are you getting 0.18 out of the jar?
Because I'm just, there's the tub is like, you know, there's like 100 pounds of candy in here, okay?
The proportion is with that number.
The
For
pro-
this
the
0.65 is the number of reds, correct?
the proportion of red candies in the giant tub is 0.165
And this is the proportion with the 200, right?
of the 200 pieces of candy, right? So when I draw a sample out of this, right, I could get more, you know, some more red candies. I could get a fewer. I mean, it's possible that a random sample, like a small sample, could end up being entirely red or something like that. So the sample proportion could be something different, okay? And so anyway, I go back and I draw a second sample, and I get another p hat, okay? And then I go back to the population and I draw another sample, and I get another p hat, okay? And so we just continually repeat this process over and over and over again, okay? So repeatedly draw samples, okay? And every time we draw a sample, we calculate p hat, and we record it. Calculate and record p hat, okay? And so after doing this thousands of times and keeping track of all the different p hats we have, we are going to look at the distribution of p hat, okay? What is the distribution of p hat? Okay, and so, you know, here I took out one scoop and I got proportion equal to 0.18, okay? we'll say, you know, another scoop. Okay, and this other scoop of 200 candies, maybe I get a proportion of 0.16. Okay, and then another scoop, and maybe my p hat ends up being, I don't know, 0.145 or something like that. Okay, and we're going to keep track of all of these different p hats that we observe. Okay, all right, so conceptually, does what we're doing make sense? Okay, and we're going to and the idea is we do this like thousands of times. Okay, and we're going to keep track of every single p hat we observe, and then we want to ask, what is the distribution of p hat? Do I get large values of p hat? Do I get small values of p hat? Are certain values of p hat more common? These are the kinds of questions we're asking. What is the average p hat that I see? What's the standard deviation of the p hats I see? Okay, because we're going to record thousands of different p hats. Okay, and so to do this, we can run a simulation. Okay. Okay, and I want Reese's Pieces. Okay, so here I've got, so in this simulation, we're going, this is like a big tub, and it's full of not M&Ms, but Reese's Pieces candies. Okay, so Reese's Pieces are kind of like M&Ms, but they have peanut butter inside. All right, and they come in 3 colors: brown, yellow, and orange. All right, but they look a lot like M&Ms. Okay, and so this is a computer simulation where it's going to basically mix up all of these pieces of candy, and they're going to come out of the machine, and it will sort them between yellow or orange versus yellow and brown. Okay, and what we're interested in is what is the proportion of candies that are orange. Okay, and so I'm going to draw out 50 pieces of candy. All right, and it says the probability of orange is 0.3. So if we were to look into this machine and count exactly how many are orange, it would be 30% orange. Okay, and so the simulation is running. The pieces of candy come out. All right, and it says, whoops, the number of orange candies is 16. 16 out of 50 would be 32%. Okay, and so when we're going to keep track of it, and so on our we're going to build up a dot plot here, and on our dot plot we put a dot right at 32%. Okay, and so I'll do this again. Okay. All right, and so this time, out of the 50 pieces of candy, only what is this? 10 ended up orange. Okay, so the proportion that's orange, p hat, is equal to 0.2. Okay, and so I record a number. I put a dot right here at 0.2. Okay, and then and so we can run this thing over and over again. Okay, and so this time I count them up. 14 are orange. 14 out of 50 is 28%. We put a dot at 28. Okay, and we just do this, and this time we got 18 orange. If we count them up, 18 out of 50 is 36%. We record that. Okay, and so we can continue doing this, and every time we record another dot. Okay, this time 18 are orange, and so we get a second dot at 36%, and so we see a small stack forming here. Okay, and then Okay, and here, 32% shows up again, and 24% shows up. Okay, so this is the distribution of the p-hats that we got after taking 10 of these samples. Okay, but we want to do this like thousands of times. Okay, so I can kind of speed this up. I can say, draw 10 samples at a time, and then we'll see the machine spin, and it's going to just basically throw 10 additional dots here. Okay, but can you guys see the process that's going on? Okay, we're just adding one dot to the thing. Now I'm going to add 10 dots, but basically each of these dots represent drawing candies out of the machine, counting up how many are orange, and plotting that proportion. Okay. So after another 10 dots, we have a total of 20 dots in our dot plot. Okay, we see certain values are appearing a little bit more commonly. Okay. Okay, so this is after 100 simulations, we see certain values, 30, 32%. These show up quite often. A lot of these are showing up quite a bit. We're not getting very many values out here. Let me, we'll just continue running this simulation over and over again. So again, we're repeatedly drawing samples out of the population and calculating the p-hats. Okay, so this is after 200, 300. So after 500, the dots have gotten so close together that they basically have merged into lines. Okay, and that's okay. We can still kind of compare the relative heights of these lines. Okay, so after 1,000, it becomes clear that values close to 30%, like 28%, 30, 32%, these are kind of the most common values, which makes sense because the proportion that's in the actual machine is exactly 30%, okay? But then, yeah, when you draw a random sample, it's possible to get a few more or a few less proportions in here, okay? And so we've got, maybe I'll... Okay, so after 5,000 samples, we have this shape here. Okay, maybe I'll do another 5,000 here. Let's see if the okay. Okay, and so after 20,000 samples, we get this kind of shape. Okay, what does the shape of our distribution look like to you? Yeah, it's unimodal, symmetric. It looks very much like the normal distribution. Okay, I can actually plot a normal distribution on top of it. Okay, and we can see that values close to 30% are quite common. Values a little bit below it, or values close to that are less common. But then values that are very far away, these happen very seldom. Okay. All right. Is this okay? The creation of the sampling distribution. Okay. All right. So the sampling distribution is the distribution of p-hats, okay? This is, each time we take a random sample from the population, the sample proportion p hat can vary from sample to sample. Okay. Our simulation and mathematical theory, which, you know, we're skipping the theory part, but the mathematical theory also backs this up, shows that values of p hat that are close to the population proportion p are most common. Okay. Values that are far away from p are possible, but less common. Okay, I'm going to just take a screenshot of this and throw this in the notes as well. So right here, let me just kind of draw this. This is the population proportion P. Okay, this means in the giant machine, okay, and then this is the sampling distribution. And what we see is, you know, values of p hat close to p are common. Values far from p are less common, okay? All right, and so again, the idea is in the population, there is some proportion p. In this case, 30% of the candies are orange. When we take random samples out of that population, our random sample can have a different proportion. The sample proportion could be 30%. It could be a little bit higher. It could be a little bit lower. Okay? And what we see is that if we do this over and over again, we find that values, the sample proportions that are quite close to 30% are going to be the most common values, or sample proportions that are far away from 30%, like 40% or 42%, these are much less common than values that are close by. Okay, and so this shape, the shape here, is shape looks a lot like the normal distribution. And so what we're going to say is that we can approximate this thing. This thing is the actual sampling distribution. And what we're going to say is we can approximate the sampling distribution using the normal distribution. Okay? And this will simplify a lot of our problems because getting the actual sampling distribution would be really, really tedious for us to calculate. Okay? And a little bit more complicated than what we would probably want to actually deal with. So if we say, well, I'm good with a pretty good approximation, okay, and it's and the approximation is going to be very, very good, okay. We can answer a lot of our questions using the normal distribution, okay, which is a lot easier to deal with than the exact distribution. Okay. All right, and so we can approximate the exact sampling distribution of p hat by using the normal distribution. Okay, there's mathematical theory that backs up this this thing, and that mathematical theory is called the central limit theorem. Okay, the mathematical principle that allows us to do this is called the central limit theorem. Okay, the central limit theorem makes a couple assumptions or has a few conditions that have to be met in order for it to work, and so we'll talk about those. Okay, you know, there are a few conditions that must be met. Okay, and basically the central limit theorem says that the sampling distribution of p hat can be approximated with the following normal distribution. Okay, so it'll be normal with mean equal to p and standard deviation equal, and it's just a slightly ugly number, or ugly formula, but not too bad. P times 1 minus p divided by n inside the square root. Yes, question?
Is that formula the standard deviation or?
It's the standard deviation of the sampling distribution.
And standard error?
It's also called the standard error, yeah. This formula, This thing is also known as the standard error. I guess I'll put that in here. Also called the standard error, okay? Okay, but it's basically the standard deviation of the sampling distribution. All right, does this, so far so good? Okay, maybe? All right, well, let's try a problem out, make sure we understand this. Okay, so I've got we're gonna go back to our tub of M&Ms. Okay. M&Ms inside the tub the proportion of red is 0.165, okay? We take a random sample of 200 candies, okay? So I'll kind of guide you through this. Okay, so the question will be, all right, we will look at the sample proportion p hat. All right, well, sample proportion p hat. Okay, so over here we're going to ask, what is the distribution of p hat? Okay, meaning it's going to be normal, and what will the mean and what will the standard deviation be? Okay, and then the second part is, once you figure that out, we're going to ask, what is the probability that a random sample of 200 pieces of candy will have a proportion of 0.2 red or more. Okay? So go ahead, get this written down, try this out, and so I'll pause the video here. Well, I guess before I pause, I just want to make sure we understand what the question is that's being asked. Okay? So, you know, here I've got M&Ms in the, I'm drawing all these candies in here. We've got M&Ms in the tub. Inside the tub, the proportion that's red, 16.5%. 0.165 are red inside the tub. Okay? I'm going to take a scoop out, 200 pieces of candy. All right? When I take this scoop out, I could end up getting lots of red candies. I could also get very few red candies. It's just a mix, right? It's just a random mix. And so my question is, what's the probability that my scoop, my random scoop of 200 pieces of candy, ends up being 20% red, okay? Because the tub is only 16.5% red, or 0.165, but I'm saying, if I take a random scoop, could I get 20% red or more? And if so, what's the probability that that's going to happen? Okay. Does that question make sense? Okay. All right. And you're going to basically use the central limit theorem, or this information on the previous slide, to answer this question. So go ahead and try that out. I'm going to pause the video if you're watching on YouTube. So I would advise you to pause it so you can work on it as well. Okay. Oops. All right. So I know a lot of you guys are still working. Just want to make sure that we're getting off to the same start here. Okay. So we've looked at this. We should have identified this as our P. Okay. And so the normal model has a mean equal to P. So our mean is going to be 0.165. Okay. We're going to take a random sample of 200 candies, so our standard deviation is P times 1 minus P over N, 0.165 times 1 minus 0.165 divided by 200, okay? When you plug that into your calculator, so when I hit square root, 0.165 times 1 minus 0.165. I did a 2, thank you. Divided by 200, okay? I get 0.0262. Okay, so this is my mean and this is my standard deviation. Okay, so let me give you some guidance on how to do this part of the problem. Okay, so here it says, we're taking a random sample of 200 when we want to know what is the probability of getting a proportion of 0.2 or more. Okay, so here this now becomes just a regular old normal distribution problem. What is the value that goes right here in the middle? The mean, right? The mean of 0.165. This goes right here in the middle. Okay, and here the question is asking 0.2 or more. So I'm going to draw a picture right here where I'm going to draw a line at 0.2, and I want to know 0.2 or more, so I'm going to shade to the right. Okay, so I will pause right here again, and you guys can figure out the answer to this part of the problem. Okay. Okay, let's come here. So the first thing that we will want to do is we will want to find a z-score. Okay. And so the z-scores are where we are, the distance from the mean in standard deviation. So I'm going to do 0.2 minus the mean, 0.165. And I'm going to take that distance and I'm going to divide it basically by my standard deviation, which is 0.0262. I guess I could keep a few more decimals here. And so when I punch this into my calculator, I'm going to type in 0.2 minus 0.165, parentheses, and then I'm going to just hit divide by the answer, because the answer that was in the calculator was the standard deviation that was already in there. Okay, so I don't have to retype all of these numbers. Okay, and this gives me a z-score of 1.33. Okay, maybe you rounded off your number and you got 1.34 or something, but something very close. Okay, your z-score should be something around 1.33. Okay, you guys still with me?
No, why did you divide it by 0.02646?
26246. So I did, so I did 0.2 minus 0.165. Okay, and then I'm going to divide this by the standard deviation, which is 0.026246, I think. Why? What do you mean why? So, well, okay, so in the previous part of the problem, we established that the standard deviation is this number, right?
Yeah.
Yes. So the z is
Okay, got it. I got it.
this minus the mean divided by the standard deviation.
Okay.
Yeah. Yes.
I know that on like one of the quizzes and possibly on the midterm, when we did questions like this and we had to find the z-score, we would want to round up. With it being 1.335, should we round it up to 1.34? Can we leave it?
Okay, so I would say either is fine. Yeah, 1.33. So it depends how many decimals you kept in your calculator. That's gonna kind of decide what for this thing. If you use 0.0262 and you didn't keep the 4.6, then you probably got 1.34. If you kept the full number, it would come out closer to 1.33. Either is fine. Okay. Yeah. Yeah, we will do that, okay? So we're going to look up z equal to 1.33, okay? And the area to the left of 1.33 is 0.9082, okay? So the area to the left of 1.33 is 0.9082. And I want the area to the right, so this is going to be 1 minus 0.9082. This gives me an area of 0.0918. Okay? And so the answer to our question is about 9%, meaning inside the giant tub, is 16.5% red. Okay? When I take a random sample of candies, I can get more red, I can get less red, okay? The question was asking, what's the probability I'm gonna get 20% red? Well, I'm gonna get 20% red with a probability of about 9%. So it's not gonna happen very often, but it could happen. Is that okay?
Let's say if you're asking before for standard, for standard normal deviations, we use SAT scores a lot, so
Yeah.
that goes in my head score minus this.
Yeah.
But in this case, it was the proportion that you gave us.
Yeah. The
Proportion of 0.2. So that would be the.
right. We're asking what's the probability of getting a certain proportion now? Okay. Is that all right?
It wasn't really easy.
Okay. Well, let's try another one. Just make sure we have this. Okay. All right. So we'll do another problem. Okay, so I'm going to say, so we'll say in the United States, USA, I don't know, making up numbers, we'll say 30% of households own a cat. I don't know if that's true, all right? But we'll just say 30% of households own a cat, okay? You randomly select we'll say 150 households. Okay. What is the probability that your random sample has less than, we'll say, 25% of people, or 25%, we'll say, cat owning households? Okay, go ahead and try this out. So just to give you some guidance, you'll want to start by figuring out the distribution of p hat. Okay, so begin by figuring out the distribution of p hat. So you'll need the mean and the standard deviation. And then you'll use those to answer this question. Okay, and again, I'm going to pause the video. So if you're watching on YouTube, pause it here so you can try to figure this out yourself. I will begin going through the answer. All right, and so, as we go through the problem, sometimes it's helpful to identify what's P and what's N and what's the stuff we're looking up here, okay? So here it says, in the USA, 30% of households own a cat. So this is talking about the population. And the population proportion is 30%. So here, our population proportion P, maybe I'll use a different color. Population proportion P is 0.3. Okay, it says we're going to take a random sample of 150 households. So here, our sample size is 150. Okay, and here we want to know what's the probability that less than 25% end up being cat-owning households. Okay, so this is our particular p hat. Okay, the p hat of our sample. Okay, and so when we're talking about the distribution of p hat, the mean is going to be p, and the standard deviation is p times 1 minus p over n. So our p is 0.3, and our standard deviation is going to be p 0.3 times 1 minus p divided by 150. Okay, so I'm going to do square root of 0.3 times 1 minus 0.3 divided by 150. I get 0.0374165, okay? Okay. If I were to draw a picture here, the picture that I have is that in the center, the mean value goes right there, 0.3, okay? And over here, I want to know what's the probability of getting 25%, which is 0.25, or less. So I want to know what's this area over here. So I got to figure out my z-score. My z-score is going to be 0.25 minus 0.3 divided by our standard deviation, 0.037417, or whatever that is, okay? So I do 0.25 minus 0.3, close off the parentheses. I'm going to just hit divide by the answer key. Okay, and by coincidence I get negative 1.336, which is very close to what we had last time. I'm going to round off to negative 1.34, okay? But Okay, and then so, I go to the z table and I look up, what is the area to the left of negative 1.34, and I get 0.0901, okay? So this answer right here, 0.0901, okay? So it is a coincidence that it was very similar to our last answer, but this is the process by which we solve these problems. Yes?
Are we supposed to answer in percentage, or does it matter?
It doesn't really matter, okay? I guess, for the quizzes and the tests, it's like multiple choice, so, you pick the appropriate one. It's an expectation that you guys are able to switch from percentages and proportions or decimals easily, okay? Sherry?
So the thing where the mean equals p,
Yes.
that's confusing me. Is that just one of the givens that we're accepting?
So that is, we are talking about the sampling distribution of p hat, okay? So we are saying every time I take a random sample out of the population, the proportion that shows up in my sample could be different from one sample to the next. Is that conceptually okay? So every time I select, like, if one day I go out and I survey 150 households, maybe I get a lot of cat owners, okay? Maybe the next day I go out and I survey 150 households, I get very few cat owners, okay? And that's going to be subject to just random chance, right? So from day to day, each sample I could end up getting a different p hat, okay? But overall, if we were to keep track of all of those different p hats, overall the average p hat should be very close to the overall proportion that exists in the population, okay? So if the United States is 30% cat owners or whatever, sure, from day to day, maybe I get 25% or 35%, or some days maybe I get 40%, or some days I get very few cat owners or something. But overall, if I kept track of all of these different p hats, the average that shows up should be very close to 30%, which is our population proportion p, okay? And so that's why we say the mean is p. I hope that, okay, I hope that makes sense. All right, are we okay with this? All right, so you'll have to be able to do this on the quiz next week, okay? Okay, so we have a few conditions. In order for this to work, okay, we have conditions that say that must be true for this thing to work, okay? Conditions that must be true to be able to use the normal distribution as an approximation. Or we call this conditions for the central limit theorem. Okay, so again, the central limit theorem is what says that the sampling distribution of p hat, which is actually a little bit more complicated and tedious, what the central limit theorem says is that we can approximate it with the normal distribution, okay? So we're saying if we're going to use the central limit, if you want to answer questions about the sampling distribution, we can approximate it with the normal distribution, but there's a few things that must be true if we want to do this, okay? And so there are three conditions, okay? One is called the independent and random condition. This condition says that the samples that we use must be selected at random, okay? The sample must be selected at random. The members of our sample must be selected independently of each other, okay? Or I'll just say the individuals must be selected independently. Okay, so basically, if you're not dealing with a random sample, you're not going to be able to do any kind of inference here. Okay, we have the large sample condition. This says that the sample we're dealing with has to be big enough, okay? The sample must be big enough or large enough. Sample must be large enough. You cannot have a small sample. All right, how do we decide what is large enough? Or must be large enough. How do we decide what is large enough? Okay, so there's two ways to check. So one way to check is that the values n times p must be bigger than or equal to 10, and n times 1 minus p must be bigger than or equal to 10. Okay, and then the other way to check is that at least 10 successes and at least 10 failures. Okay. So in your data, you have to have at least 10 successes and 10 failures, or n times p has to be bigger than or equal to 10, and n times 1 minus p has to be bigger than 10. Okay, so that's the large sample condition. Basically, your sample must be large enough. Okay, and then the other one is called the big population condition. And students often get these mixed up, but one makes sure that your sample is big enough, and the other one makes sure your population is big enough. Okay, so the population must be big enough. Okay, so the population, to check this, the population needs to be at least 10 times bigger than your sample. Okay, or conversely, do not sample more than 1/10 of the population. Okay.
What does that say? Do not sample over.
1/10. 1/10 of the population, or 10%, really. 1/10 is 10%. So.
How do you define success and failure in this instance?
So those are just arbitrary labels. They're kind of like the binomial. We just said one thing is considered, quote, success. The other thing is considered, quote, failure. Again, they're arbitrary labels, so it's just you need to have at least basically 10 yeses and 10 nos. Okay? Did this happen? Yes or no? So you just need to have at least 10 of each. Okay? And all of these are basically it's a categorical variable, and you're looking at a proportion, right? So if we're asking the proportion of red candies, it's either going to be, is it a red candy, yes, or is it not a red candy, okay? And so that would be all the other colors. Is that okay? All right, let's, so let me give you a couple examples here. And you tell me which, are all the conditions met, or is a condition violated, okay? Okay, and so if not, which is violated? Okay, and so again, your conditions are independent and random condition. You have the large sample condition and the big population condition. Okay, so here's our scenario. We will say you wish to conduct a survey. Okay. So you stand at a big intersection. And interview people who walk by. Okay. You survey 210 people from, I will say, the city of Los Angeles, city of LA. You find that we'll say 40% of your sample enjoys daily exercise. Okay. Are any conditions violated? Okay, so go ahead and think about that for a little bit. Decide if any of these conditions are violated. Okay, let's see. All right, so in our case, what's the population? Los Angeles. Okay, so our population would be Los Angeles, all right? All right. So, you know, our sample size, what's our sample size? So our sample size N is 210. Okay. So is our big population condition met?
Yes.
Yes. Okay. 210 times 10 is 2010, or 2,100. Los Angeles has more than 2,100 people. Okay. Our population is big enough. That's fine. Okay. So big population met. Large sample. Is the large sample condition met?
Yeah.
So if we do N times P, that would be 210 times 40%. This gives me, I don't know, 84 or something like that? 84, okay. So that's bigger than 10. That's good, okay. And N times 1 minus P, I guess gives me 126. Okay, and that's also bigger than 10. So our large sample condition is met, okay. Are the 210 people we get, or is that a random sample? It's not, okay? We're standing at a big intersection, okay? And we get people who walk by. This is by no means a random sample, all right? First of all, we're asking people who are walking by us if they like to exercise daily, okay? We're much more likely to get people who are gonna answer yes than if we got a random sample, all right? Like a random sample would, I don't know how we would do it, but it would probably involve calling people who might never leave the house, who would never be walking around on the street, okay? People who walk on the street do not necessarily look like the entire city of Los Angeles. People who walk on the street are people who walk on the street, okay? You're not gonna get people who are unable to walk. You're not gonna get people who don't like to leave the house. You're not gonna get basically anybody who's not walking in that intersection. And then that intersection, even if it's a busy intersection, you're only gonna get people who would be within walking distance of that intersection. So you could be at a busy intersection in Beverly Hills, and the people you survey there will be very different from if you were in a busy intersection in, you know, downtown LA or somewhere else, okay? So if you're just surveying people you know, if you go to the beach and you survey people there, you're more likely to get a certain type of person than someone else. So this is certainly not a random sample, okay? So this is violated.
So what, in this case, what would a random sample, like what number-wise, what would a random sample?
Now, number-wise, a random sample doesn't depend on the number, okay?
So it's how it's worded.
It's how it's selected. How the sample is selected, that's going to determine whether it's random or not. So somewhere in the problem, it will have to say a sample was selected randomly, okay? So samples that you get by surveying people from walking around, it's not going to be random, okay? Samples you get by going on the internet and posting a internet survey poll, okay? On like Facebook, you can survey your friends or whatever. That's not going to be a random sample. Even if you put it on like CNN, it's not going to be a random sample because not the whole world doesn't go to CNN or whatever, okay? So all of these surveys conducted online are not random, okay? Yeah.
So if you're a researcher and you're trying to just get that random sample, what are you keeping in mind to eliminate all these other biases?
Yeah, so this is actually a very difficult thing to do. Getting a truly random sample in for research purposes is very difficult, and so there are a few respected organizations, but it's hard. So yeah, they have all sorts of techniques to try to eliminate bias, but ultimately it's hard to do. Okay, and that's why. A lot of times, you know, if you're following the presidential elections and stuff like that, you know, they do have polls going to these things, and a lot of times they're pretty close, but a lot of times some of these polls, the individual polls are very off, okay, and that's because it could be a result, when a poll is wrong, it could be the result of a few different things. One could be just random chance, and the poll ended up funny, right? You take a random survey of households, maybe you get a whole bunch of cat owners, okay? That could happen, okay? Or it could be they did a bad job with the sampling and they selected too many of a certain demographic, okay? I'm sorry, did you have a question there?
I did not.
Okay. Yes, you have a question.
So when it asks, the, are they independent and random? So when we get independent, is that like the P of A is equal to P of A?
No, okay, no. So independent in this case would be when I select one person, the next person I select has basically no ties to this person. So it's not like I select a person and you're gonna survey the person's best friend or spouse or whatever, okay? Because a lot of times people try to get information that way. They say, oh, thanks for participating. Go tell all of your friends to participate in this survey as well, okay? You're not gonna get an independent random sample by doing that, okay? Yeah.
Would it be fair to say for random, the second you put a parameter on it, like you say Los Angeles or TND or something like that, it's no longer random?
It could be if the population you're interested in is Los Angeles, then that's fine, okay? Then you're only going to be selecting from Los Angeles. But to get a random sample from Los Angeles, that in of itself is difficult. But yeah, if you say I'm going to interview people in Los Angeles and hope this represents all of California, then that would be a mistake. Okay, that would not be random. But if you're going to interview people from Los Angeles to represent Los Angeles, that could work if you get random people from LA. Yeah.
Would you then write you wish to conduct a survey about people in Los Angeles?
Yeah. Okay. I should probably have to write that. You wish to conduct a survey about LA people.
And then it would not be random, or?
It still is not random because the way you're doing it is you're standing at an intersection and interviewing people who walk by.
I mean, what he just said, that if it could be, if it's not random, that there's people in LA, how should you formulate the question.
So if I wanted to make this thing work, it would be like, you wish to conduct a survey about LA people. You obtain a random sample of 210 people from the city of Los Angeles. Yeah. It would need to say, like, you get a random sample of 210 people, okay? Perhaps through complicated work. But yeah. Okay. Why don't we take a break here, and then we'll come back and we'll continue on.